Alright, so we're going to talk about how conics get rotated, and a lot of our properties are still the same. We have a couple of rules that we're going to use, but in general we have conics where the axes don't have to align with our x and y axis, so we have this rotation. And really what that means is that this b term, this xy term, is not going to be 0. Before it's just dropped out and we haven't worried about it. And then we have some properties on our circle, our ellipse, and our hyperbola. And for what this called the discriminant, which looks very similar to our quadratic equation discriminant, will tell us what type of shape we have. So what we have here, right? We have our general conic section, and again we're going to have this b squared term that's going to come out. If you were to start kind of expanding pieces and factoring stuff, you would have a quadratic. So this is really a quadratic equation on y squared. You could do the same thing for x squared, and you can solve it. And so using your quadratic equation, you get your solution. It looks scary, but again, it's just solving a quadratic. It's all over 2c in this case because our a value is c, so you have a, b, c for your quadratic equation. And then we can take that piece and look at some simplifications. If we expand it all and then group our terms, we get some x squared term which deals with our discriminant. And so this b squared minus 4ac is going to be important for the properties on x squared. And so before, this is what we had again with our pieces, and our x squared, our b term was 0, and we can see our properties here. And now this is not 0. So now this b squared term exists, and we can look at our properties on it. And our properties are, if this is greater than 0, we have a hyperbola. If it is 0, we have a parabola. And if it is less than 0, we have an ellipse. And so you can kind of think about, the proof is a little bit long, we're going to look at it in a second, but not really get into it, of how this works. We know if a or c is negative, then negative 4ac is greater than 0. And in this case, so if I look at my a and my c terms, if a or c is negative, that means I'm going to have a hyperbola, right? Those values are going to be have a negative y squared or a negative x squared term, which makes the hyperbola because of subtraction. And so I can look at the same idea. If it's 0, that means a or c is 0, and I'm going to have one of these drop out. So we could say that this would drop out. I just have a y squared term, and so then I would have a parabola with one squared term. And then the last one would be my ellipse or my circle, right? If a and c are both positive, then negative 4ac is less than 0, and we would be able to see that those would both be positive, a and c, so I'd have an ellipse. And so that's some of the reasoning behind it. Now, we haven't dealt with the b squared term and how that works, but we can look at real quickly the proof. Again, it's lengthy. Our kind of take-home message is that these can be used to figure out what this shape is before we actually have to transform it as a shape. And so, for example, if we want to determine the conic section, we just look at our b, a, and c terms and do b squared minus 4ac. That's a negative value, which is less than 0, which means it's going to be a circle or an ellipse. Same on the next one, I just take my discriminant, and that's greater than 0, which means it's going to be a hyperbola. And then we can try to do this using our graphing calculator by solving the quadratic. So we take our terms, we get our y squared terms, and we factor it, a, b, and c for our quadratic formula. We're going to get a big long quadratic, and then we use our graphing calculator to get our shape, and we would see what we get, and it'd be some rotated conic as we move forward. Alright. Another way to do this is using our parametric mode and using a rotation matrix. And so depending on your familiarity with matrices, the multiplication of matrices can be a little bit complicated, but basically we have some angle of rotation, and then it's a counterclockwise rotation by some angle theta, and we have this matrix that we're going to use. So we have the parametric equations of a conic, and then we're going to use this thing, angle of theta, to get our values here for the rotation piece. So the way that that works is I would set up my rotation matrix, and then I would multiply, I'd put those pieces in, and I'm going to have to multiply that by the parent graph of this conic here. So I have two rows, I have one column. That's my parent function. That's what I'm going to actually rotate. And then I'm going to translate it at the end, which means I'm going to move it left and right or up and down after I've actually rotated. So I'm not going to put that in my rotation piece. So the way that this works is I'm going to take my values, my two rows and my two columns, and the key idea with our rotation matrices and multiplying matrices is that you have to make sure that your inner dimensions match. And so what that means here is I have rows by columns, which is 2 by 2 and 2 by 1. These have to match up. Otherwise I'm not allowed to multiply the matrices. And my resulting matrices is going to be my outside dimensions of 2 and 1. The way that this works is if we multiply it through, this is a general description of kind of how matrix multiplication works. So I would be able to multiply these. I'd get the resultant of a 3 by 2. Again, the inner dimensions have to match. The outer dimensions are what I'm left with as I multiply through. This one, my inner dimensions match. My outer dimensions would be a 1 by 3, rows by columns. So it would be a 1 row with 3 columns in it. This one wouldn't be able to work because my inner dimensions don't work. And so once we have something that we can use, it's pretty simple. We just multiply and add. So the way this works, I would take a row times a column and add those values. So I'd get 1 times 3 plus 4 times 5. And that's that piece there. And then for my next one, I would get 2 times 3 times 3 times 5. And then I get 0 times 6 times 3 times 5. And those would be, I've recreated the first column of my resulting matrix. Alright, and then for my next one, I do the same thing, 1 times 4 times negative 2, negative 1 times negative 2. I do 2 times 3, again taking this row times that, and 3 times 2 and adding them together. And then I get 0 times 1, and then 6 times 2, and I'm add those pieces together. And so my resulting piece would be this matrix here, and I can see that I've gotten a 3 by 2 resultant. I have 3 rows, 1, 2, 3, 2 columns, 1, 2. And that will be my result as I move forward. So we're going to use that multiplication property for our example before, where we're going to multiply 2. So this is going to work out where I have the inner dimensions match, 2 and 2, the outer dimensions, 2 and 1. I'm going to get a resulting matrix of 2 rows, 1 column, and those are going to actually be my final equations. So those match up. This is going to be that times that. So I'm going to take root 3 over 2 times 3 tangent t, and negative 1/2 times 3 secant t. This is my parametric mode. And then I'm going to add those together, and then I'm going to keep going with the next row and same column. I'm going to add those two together, and my resultant is going to be this if I multiply it through, and I'm going to then simplify it a little bit, right? That becomes my values as we go forward. And then what we have to do is put our final transformations at the end. So remember, we had originally we had the 2, it was plus 2 and then minus 1 in front of those. That's my x value, that's my y value. I try to graph that in parametric mode, and I should get the same rotated conic as if we did it in Cartesian form. Alright, that's it.